today. Just so for those of you who don't know me, my name's Donna Ball, and I'm a senior scientist at SFEI and the lead scientist on the South Bay Salt Pond Restoration Project. And I'm just going to introduce today four amazing speakers who are going to be talking about a project offshore of Eden Landing to reuse sediment to help feed our marshes. And really exciting set of speakers. And we'll be starting with Julie Beagle. I just want to ask everyone to please hold your questions and put them in the chat till the end. We have four speakers, and they're going to try to get through four separate talks today. So we'll answer those questions at the end of the presentation. So as I mentioned, our first speaker is Julie Beagle, who's an environmental service branch chief at the U.S. Army Corps of Engineers in San Francisco. And take it away, Julie, and then we'll have the other speakers introduce themselves at each section of the talk. Go ahead, Julie.
Thank you so much. Thanks everyone for coming, and thanks for the opportunity. I want to start out by just saying this project of shallow water placement has been a huge partnership over the last several years between us at the Army Corps, the USGS, South Bay Salt Ponds, Coastal Conservancy, BCDC, NIMS. Everybody has been involved. And so just thank you for helping us try new things in the Bay Area, including the dredging community. I see some folks on the line. We are really in the data analysis piece of this. So I'm going to give a really short update on, or just sort of a short background on what this project was, and then turn it over to my USGS colleagues to talk about, is everyone getting feedback, or is that just me?
And just everyone who's, just make sure everyone's on mute, please, if you're in the audience. Thanks.
I just want to highlight that this talk is mostly going to focus on the really hot off the press monitoring results. We're just getting them back in. We don't even have them all in. We're just processing them and sort of figuring out what they mean together. So this talk is, you're going to see our sort of like workshopping in practice, and all your feedback is really helpful. So next slide, please. So the motivation for this project comes from the fact that we have many precious existing tidal marshes in the San Francisco Bay Area that are currently projected to downshift with sea level rise and a less sediment supply. So next slide. This is Arrowhead Marsh, which you all know and love. And this is a photo from a long time ago that shows the pier at Arrowhead Marsh on a king tide and what happens to all the water birds at that time. There's no high tide refuge. There's no area for them to go. And so we all understand the importance of restoring tidal marshes. That's why you're all here, and why we all love the South Bay Salt Ponds for wildlife, but also for protection for communities and all the other benefits that marshes provide. Next slide, please. So this is older Karen Thorne's work, and she's updated this, but our marshes in general are projected to downshift over time. We have less sediment supply than we probably need for our marshes to keep pace with sea level rise. And so next slide, we're really trying to figure out how do we reuse dredged material in innovative ways that support both our bayland ecosystems that are existing and continue to support all the wonderful restoration projects that we have around the bay. So the idea is, actually just keep going, Jessie. The idea is to look at all the tools we have in this beneficial use toolbox. We've done a lot of direct placement of dredged material at Montezuma, Cullinan, Hamilton, Sears Point, etc. And we're looking at how do we support existing marshes using this idea of strategic shallow water placement. The idea of this mimics the way that sediment naturally transports between the shallows and the marsh, being resuspended by wind waves, moved over the mudflats and the marsh at daily tides or extreme water levels in big wind events often, and then is trapped by vegetation. So next slide. So this project that we tried, now coming up on a year and a half ago, was trying to mimic or boost that natural sediment supply for existing marshes by placing placing sediment in the shallows just offshore, and then monitoring how that sediment would move across the shallows, mudflat, and marsh, etc. So as we all know, our bay is heterogeneous, and this type of tool is not necessarily suitable everywhere. So we did a lot of work trying to figure out where are the places where this type of offshore, nearshore, shallow water placement could be suitable. These are the types of things we were thinking about. I'm not going to go through all of them, but ideally, where is a place where we could place sediment offshore and it would move generally toward the shore? Where are places where we could avoid, for a pilot study, avoid other types of habitats, just to try to separate, since this was the first time this was being done in San Francisco Bay. So we tried to avoid large eelgrass beds or nearshore reef projects. We tried to focus this on places that had had less investment over time. And so I'll keep moving, but there's a lot more to say on that. We chose 2 sites that met those criteria to do initial modeling. We used the UNTREM Bay Delta model through Anchor QEA to model and try to figure out, we had one place to test this. Where was the best place to start? So through that modeling, we determined that Eden Landing would be a good place. Also, Karen and Jessie in the USGS had done so much work there. And so there was a lot of background data. We tested different volumes. We tested different locations. We tested different seasons. We were also thinking about what type of equipment could be used to take that material from a federal dredging channel over to that location. The bay's super shallow, so we were really limited in terms of equipment. So there's a lot of considerations going into how to actually do this for the first time. And I really want to say that the dredging community was super helpful in thinking through what was possible. And we will continue to need to build those partnerships if we want to keep testing these types of new beneficial use types of tools. Next slide. So in December of 2023, we took 90,000 cubic yards from the port of Redwood City. Next slide. That was loaded into the shallow draft scows. There were 2 sizes of scows. This is what a filled scow looks like. Those scows were pushed across the bay. We did this 169 times to this placement location grid that you can see in blue on the left side of your screen. Next slide. This is what on the left, an open scow. So it's a bottom dumping scow, and it just basically deposits the material on the bay shallows on the floor. And this was at 9 to 12 feet of depth. So pretty shallow for a heavily loaded scow. So they had to be light loaded. And that was the placement. That was the study. We had a lot of work went into the monitoring questions of how do we know what happened when we did this. We had 2 major questions that then our USGS colleagues, and then there's other people that also did other types of monitoring. So we're going to focus on these 2 questions. One was, what are the potential impacts on the benthos and the ecological communities nearby? You can imagine that when you place sediment on the bay floor, there's impacts to the critters that live below in the bay muds. There's also eelgrass sort nearby, and so we monitored that. We wanted to understand how long do those effects last and how far do those effects spread. So Susan's going to talk about that. But first, next slide, Jessie's going to talk about how we kind of thought about where does the sediment end up and how do the physical processes influence its transport. And we tried a lot of different monitoring methods with this. And part of this idea of a pilot is trying to figure out what are the monitoring techniques that were the most effective that we would want to duplicate, iterate on as we try to move forward with this approach. So I will turn it over to Jessie, and I'm right on time.
Thanks, Julie. I'm Jessie Lacy. I'm at the Pacific Coastal and Marine Science Center of USGS in Santa Cruz, and I've been working on this with a number of scientists here, in particular Andrew Stevens, who's co-leading with me, and Rachel Allen and Sam McGill. So as Julie said, our focus was on the physical processes part in the shallows. Whereas Karen was working on marsh top, and we are interested mainly in where it goes, but a little bit on impacts during placement, as I'll talk about, but specifically on the evolution of the bay floor. So the components, the monitoring components I'll be talking about are repeat bathymetric surveys, oceanographic data collection, and sediment sampling, the physical properties of the sediment. So as Julie explained, the placement took place in December of 2023. And one of the great coordination things that happened is that we were able to get very specific information from the dredgers about exactly how much sediment they placed and exactly where they placed it throughout the project. So you see in that image in the middle that the top third of the placement area was never used. All those blobs represent individual placements, and the color, you can see what the color means by the plot along the bottom. So they moved from the south to the north, and the placement was within the placement area, which for me was a question whether that would even work. So the total volume placed was 74,000 cubic meters. So I just want to talk a little bit. So just based on bulk density of the material on the bed, we can say that's about 36,500 tons of mass as opposed to volume, just converting from volume to mass. I just want to talk a little bit about how much sediment is that in the bigger scheme of things. So we've done quite a bit of work on accretion rates in Whale's Tail and Cargill. And so based on that previous work, so this represents about 15 years of accretion on combined Whale's Tail and Cargill marshes. Or you could think of it as about 20 years of lateral erosion of that Whale's Tail marsh scarp. Or if you want to think more about, in the bay, if you think about the suspended sediment, when it's wavy, how much suspended sediment is in the water column in a sort of 3 kilometer by 3 kilometer area, which is sort of the area between the placement area and the marsh. It would be about 10 times that mass of water. So we have a huge amount of sediment just coming up into the water every day, just naturally. Or if you thought about the amount of sediment traveling across a 3 kilometer transect, it would take about 36 days for that same mass of sediment to cross that transect. That would be sort of an average. I'm not talking about the tidal flow each way. I'm talking about a tidal average. So that just gives you kind of an idea of that this, how this mass measures up against what's out there already. So getting back to our data collection. So we monitored waves, currents, salinity, suspended sediment concentration, and wind speed and direction in the region of the placement area from November, so for a month before the placement and through the following July. The wind and wave was actually for longer, but for that November to July period, we had a number of stations, which you see in the plot in the lower right, kind of surrounding the placement area. We couldn't be in the placement area because we didn't want our instruments to get dumped on. So one of the questions was, to what degree do the placements increase or increase turbidity? And of course, we're concerned about that because higher SS suspended sediment concentration or turbidity reduces light penetration, which is a concern for all plants, specifically eelgrass and phytoplankton. So what we saw was that there were spikes in SSC after many of the placement events, and those spikes typically lasted about 1 to 1.5 hours. So in the upper panel, you're seeing the tide stage, and in the lower panel, you're seeing SSC measured at 2 stations. So the orange one is offshore of the placement area, and the green line represents onshore of the placement area. And so what we saw is that we really only saw those spikes at the closest station in the direction of the tidal currents. And what I mean by that is that when there was a placement on an ebb tide, we saw it at the offshore station. And when there was a placement on the flood tide, we saw it at the onshore station and not at the offshore station. And furthermore, the elevation of the sediment was to levels that we see commonly during wave events. In fact, during the biggest wave event, we saw suspended sediment concentrations of 1 gram per liter, but we commonly see this sort of 200 to 400 milligrams per liter for up to 12 hours. So while it clearly increased sediment concentrations, we conclude that it was for short periods and without exceeding levels that occur naturally. So just here's another example of a spike that occurred during a flood tide at the X2 station. And what you're seeing in the right-hand panel, those 2 blue lines are the calculated trajectory of water and suspended material from the placement location, which again, we knew from the dredgers, following that placement. And we're calculating that trajectory based on the currents measured at the X2 station. So we collect data every 15 minutes. So those numbers correspond to the number of measurement intervals following the placement. And what you see is that at interval 3, so in other words, 45 minutes, it's predicted to reach the X2 location. And when we go back to the suspended sediment concentration in the lower panel, we see at time 3, there's this clear spike in sediment concentration. So this is just confirming that that spike that we saw was in fact associated with that plume. So to determine the evolution of the bed and what happened to those mounds of sediment that were placed, we used repeat bathymetric mapping. And whereas the initial plan was to spread a relatively thin layer of material throughout the placement area, what we actually saw was multiple mounds of varying size. And then we saw that the height and volume gradually decreased. So the maps on the right are maps from 6 different surveys. We've actually done 8 surveys at least. But so the first one is before the placement, and then you see over time the appearance of the mounds, and then they gradually get smaller. And in the lower middle part, though, that's now transects across one of the biggest mounds, which is shown by that black line on the maps. And you see that the height gradually decreases over time. And what we found is that the taller mounds have in fact eroded more than the smaller mounds. So this here we have in that plot, we have the change of height on the y-axis and the initial mound elevation on the x-axis. And we see that the mound that was the tallest, the top of it was the tallest at the beginning, has changed the most. And whereas, so that one has changed by about 50 centimeters, and that's just in the first 6 months. And then that whole other group of mounds had eroded by more like 20 to 30 centimeters. So now when we think about the total volume in all the mounds, what we see is that the rate of change decreases over time. Our initial survey captured about 67% of the placed volume. So placement went on for an entire month or 26 days. And we couldn't survey till afterwards because we couldn't be out there in the middle of all the scows. So what we measured at the beginning is about 67%. Of course, there's an error bar on that. So let's just say roughly 70% of the total. And that difference means that there was erosion of some of it before we got out there, and some of it dispersed in plumes, as I've shown you. And then a year later, in January of 25, we were down to 42% of the placed volume. We will be doing an additional survey in January of 26, so we'll be able to see what happened in the second year of the post project. So again, what we see is that the taller mounds are eroding faster than the shorter mounds. So here I'm showing you 2 mounds shown on the right in blue and red. So these were mounds that were placed quite late in the placement period. And the tall one, what you see is the round circles represent the 95th percentile, and the triangles are the 50th percentile in height. And you see that that blue mound, the tall one, eroded much more quickly at the beginning than later, and also much more quickly than the shorter mound. And this is what we expect because the higher mounds are exposed to more wave energy. And it also, it kind of supports the idea that I already mentioned, that probably the peaks of the mounds placed earlier eroded before the first bathy survey. So what did those sediments look like? We sampled at 5 different locations in the placement area before and after the placement, and then some of those locations ended up being within mounds and some were outside mounds, just by chance, really. So what we see is that, so the before the, let's see, blue represents outside the placement area, red represents within. And what we see is that outside the mounds, I should say outside the mounds, not the placement area, outside the mounds, there's no change in the sand silt clay fraction, and the bulk density was not significantly different. whereas within there was clearly more silt, less sand after than before, and the bulk density was significantly lower. So what we see in the place sediments are less sandy, lower in bulk density, and less shell hash. And here are some images of what they look like. Outside the mounds, the sediments are chock full of shell hash. There's lots of algae, tube worms, and within the mounds, it's very homogeneous. The sediments are easy to penetrate. It's easy to sample there, whereas outside it's quite difficult. I see that I am going late, so let's see what we have here. Maybe we'll just go to this, my last slide. So we use the current data and the sediment data to calculate the suspended sediment flux. So we're interested in where is the sediment going? What direction is it going from the placement area? And I want you to focus on the black arrows here, which represents the total flux. And if we just look at all wind conditions for this 4-month period, including the placement area and through to April, we see that the average flux, so this is now the average hourly flux for the full period, is to the north and a little bit to the east. So not great for getting to the marsh. And if you look only at calm conditions, so this now represents the transport that's produced not by waves and not by wind, but by the sum effect of tidal currents, estuarine circulation, bathymetric effects, all the other effects that influence currents. You see there is a smaller but consistent flux to the north. Now, if we look at windy conditions, which is when more sediment moves, and now it's broken down by direction of the winds, we see that for some wind directions, specifically from the northwest and the southwest, again, if you look at the dark arrow, you see that flux is toward shore. So even though the average is to the north, there's times where it's directed shoreward. So we see that the greatest flux is when winds are from the southeast, and it is again to the north. However, that didn't occur very much. It's only 18% of the time. Whereas when winds are from the northwest, which will happen 26% of the time, we do see shoreward flux. And there is also somewhat shoreward during southwest winds. And then, of course, during the summer, we would see those northwest winds even more frequently. So I think I've made my conclusions clear as I've gone along, and I don't want to eat up more of Karen and Susan's time. So I think we'll just move on here to Susan's section. Thank you.
Okay. Thank you, Jessie. Yeah, I'm Susan De La Cruz. I am a research wildlife biologist with the USGS Western Ecological Research Center, and our team included Isa Wu, Tanya Graham, and Lori Hall. And we were tasked with evaluating the effects of the project on the benthic community, which is a fundamental component of essential foraging habitat for many of the fish and bird species that are using this shallow subtidal area. So in our study, we were measuring both the structural and functional metrics to assess impacts. Structural meaning like taxonomic composition and density of invertebrates at a site. And they're among methods that are commonly used to evaluate benthic recovery after dredging. But we're also using functional metrics like macroinvertebrate biomass and energy that's available to predators to give more information about the role that invertebrates play in the ecosystem, providing trophic support for consumers. So both of those metrics can recover independently from one another, and there's a growing interest in applying them to evaluate recovery of habitat quality. Okay, now next slide. So our key questions for the project were essentially, does the thin layer placement have an immediate impact on benthic communities and foraging resources for fish in the shallow subtidal? And then second, what is the spatial extent or the distance from placement of any of these effects on the community? And third, how long does it take community structure and function to kind of recover, if anything happens at all, back to pre-placement conditions? Next slide. So to complete our functional assessment, we're borrowing from a method called the Benthic Resources Assessment Technique, or BRAT for short. And BRAT was specifically developed as a quantitative tool for evaluating dredge impacted sites in terms of trophic support for bottom feeding fishes. So it integrates information on foraging ecology and prey profitability, and it's used to estimate energy that's available to specific fish species. So the conceptual model kind of shows that. For example, we have English sole and leopard shark of different ages, juvenile and adult, and it shows that there's different accessible sizes and depths of prey for these species and ages. So implicit to this framework is the idea that an increase in biomass or energy content of the prey at the right size and depth for a target fish is going to increase habitat function. And in San Francisco Bay, we've modified the BRAT a little bit to focus specifically on the ecology and diets of local species. And then we've used that before in previous studies of effects of dredge removal, actually. And then another thing that we did was apply a before-after control impact, or BACI, design to our study. It incorporates, pre and post sampling at a treatment and a nearby reference location. Oh, yeah, thanks for the next slide. So that was really essential because it allows us to distinguish any background environmental or seasonal changes from the placement. And to choose a control area that was similar to the placement, we had to evaluate sediment characteristics and elevations and benthic communities around the placement area. And after doing that, we selected that area that you see in green just north of the San Mateo Bridge as an appropriate reference. And then to understand recovery time, we sampled during 4 periods. We looked at immediately before the placement, immediately after, or 0 months, and at 6 months and 12 months post-placement. For sampling configuration, we landed ultimately on a uniform design where we're sampling locations every 50 meters to kind of try to blanket cover most of the potential placement area, because we really didn't know, even though the plan was to spread the sediment out evenly, as you saw from Jessie's talk, that didn't really happen. So it wasn't guaranteed, and we wanted to ensure that we covered areas where the placement occurred. And then lastly, we included those short transects extended towards shore to evaluate distance effects. Okay, next slide. So we've completed sampling at all 4 time periods. Our field sampling consisted of taking 10 by 10 centimeter cores. We partitioned those by depth, top 5 and bottom 5 centimeters. We took cores for sediment grain size, and then we continuously monitored water salinity and temperature. And then the lab right now, we're identifying macroinvertebrates to broad taxa. We're size classing the invertebrates and measuring biomass and energy density for that functional assessment. And those are the data that I'm going to focus on today. But in a subset of the course, we also are identifying inverts to the lowest taxonomic level, so we can do a complete assessment of community structure, which I won't talk about today. Next slide. So as I mentioned, we're still really in the middle of processing samples, and I'm just going to present today preliminary results from 25 samples, 25 locations that were sampled like before, at 0 months and 6 month time periods. And they're within that red box where Jessie talked about the sediment mounds here in the treatment area. And then there's another red box, an analogous box around the same area in the control section that we'll be comparing to. Next slide. So here we're looking at mean densities of broad taxa in the top 5 centimeters of the core. And we found that 7 broad taxa comprised like 97% of the invertebrates that were found, and that the taxa were really similar between treatment and control areas. So that's good, a good match. We found that total macroinvertebrate density was not different between treatment and control before the placement, but then it was significantly lower immediately after dredge placement in the treatment area. And then at the 6-month time period, invertebrate density in the treatment area popped back up, and it was not different from the treatment area in the before time period. We do not have all the control samples analyzed. This is definitely a work in progress for that 6-month period. So we can't, compare what the treatment looks like to the control right now. But interestingly, we're seeing a change in the taxa composition at 6 months with amphipods, which is a taxa that can rapidly colonize after disturbance, kind of dominating the area. So when the control samples are complete, I think we'll have more clarity on whether these amphipods are more of a seasonal, represent kind of a seasonal pattern in the region, or they are a response to the sediment placement and recovery. Quickly looking at the 5 to 10 centimeter depth, just pointing out polychaetes. Thanks, Jessie. I'm forgetting to tell you to switch. Pointing out polychaetes are the dominant taxa at this depth, and that we really didn't see between before and after a significant difference in taxa density between the treatment and control. Next slide. So now we're looking at invertebrate energy content in the top 5 centimeters of the sediment, and we see that bivalves and polychaetes provide the greatest proportion of energy in both the treatment and control areas. So mean available energy was significantly greater in the treatment compared to the control in that before time period, before anything happened. But then it flip-flopped and was significantly reduced in the treatment compared to the control immediately after the placement of sediments, suggesting that there was an impact on benthic energy. And we're still seeing the kind of those lower values in energy in the treatment area at 6 months. But again, we need the control samples to understand that better. I wanted to point out that there's a tiny blue line at the bottom of the 6-month treatment bar, and that represents the amphipod energy that we're seeing being put into that. So all those amphipods that bloomed in the 6 months are providing less energy, but there's more. So next slide. Now we're looking at bivalve size class, and that could help explain some of the energy results we've seen so far. So here you see invertebrate sizes on the x-axis and density on the y. And note that in the treatment area prior to the sediment placement, there were some really large bivalves that were clams, and those have high energy values, and some of those seem to have been lost immediately after placement. And then at 6 months, this is all circled in blue, you see some of these clams start to return, but they're at smaller size classes. They take a while to grow, and therefore they're providing less energy. And you see the small sized amphipods, which are great prey. They're easily consumed by almost all the predators out there, but they provide less energy. So as these clams start to grow again and reach larger size classes, we're expecting that energy they provided will rebound back. In the control area, we really didn't see changes in the size class of the taxa. Okay, next slide. Next and almost last. And so why do we care about energy and size class at all? Well, remember back to our functional assessment of the MBRAT. And this table is from a previous study, and you can see we were able to use measures of prey size, depth, and energy to calculate a % reduction in biomass and prey energy between a dredged and an undredged sampling area for a range of taxa adults and juveniles of various fish that are covered under federal fishery management plans. So that's our end goal, and that's why we're bringing together all these data. So there's going to be more to come as we put it together. So just the take home is that our preliminary findings are suggesting that invertebrate density was initially reduced but rebounded in the top 5 centimeters after 6 months. We didn't see changes in the lower 5 centimeters. And energy density and size class of bivalves might be slower to rebound, meaning that functional recovery might take longer than 6 months after placement. But again, caution is required because this is ongoing work, and we really need the full data set to understand the response of the benthic community. We have some really neat results on distance effects, but we'll have to save that for a later day. And the very last slide, Jessie, is on eelgrass impacts, which our team didn't measure. This was done by Merkel and Associates, and they looked at eelgrass aerial extent and density pre-project in October 2023 and then post-project in April 24. And they actually saw an increase in the aerial extent of eelgrass by 80% and a 27% increase in eelgrass density. So looks like a good sign for eelgrass. It doesn't seem to have been affected. Now I will pass it to Karen.
Hi, good afternoon, everyone. So my name is Karen Thorne. I work for the USGS Western Ecological Research Center, and I'm based in Davis.
Karen, we can't hear you.
Oh,
That's better.
can you hear me now?
Yes.
Okay. Okay, my name is Karen Thorne, and I work for the USGS Western Ecological Research Center based in Davis. And our part of the project was measuring the marsh and tidal restoration areas to see if there is detection of the sediment placement. So quickly, I want to acknowledge the team here that really did a lot of the work you're going to see today. Next slide. So our key question was, where did the sediment end up? So we monitored the marsh and the restoration. We did it in two ways. One was a particle tracking study, which I'll talk about at the end, and understanding sediment deposition and accretion in the marsh before, during, and after sediment placement. Next slide. So for the sediment pads, we had 12 transects. You'll see a map soon of where those located. There were different stations by distance from the tides or the water. Each station had 3 replicates. You can see the picture there. We collected this data for 15 months. So right before placement and then a year and a half, basically, after placement, not a year and a half, a year and a few months. And then we collected the sediment that's deposited on these pads monthly and determined the deposition rate. Next slide. Alongside these sediment pad stations, we also put down marker horizons. We use feldspar. It's a natural occurring clay. We put it down and it creates this really nice line. So you can see how much accretion has occurred over time. So that's a continuous measurement once it's placed, and it becomes sort of integrated of what gets deposited, what gets moved around, and it's sort of an integrated measure over the whole time period. Next slide. So this is what the sampling stations looked like. We had sediment pads out on the bay edge and then up through the creek back to the restoration area. We had over 2,000 sediment pads collected over the study period, and we had 48 sampling stations using feldspar. Next slide. So this is what it kind of looks like. You know, sediment pad studies are kind of low tech, but a lot of work. And so you can see a picture there, what it looks like. So that's how much deposition occurred at that location over 1 month. And looking at all that data together over the sampling period from October 2023 through December of 2024, you can see this is how much sediment was deposited in the marsh surface each day. So you can see that in those summer months, which Jessie tells me is the windy season, that we had the highest rates of deposition. And then normally it tailors off in the winter, but in December of 2024, we actually had some pretty big storms come through. So you can see that sediment deposition peaked again in that winter. Next slide. So this is what it looks like by transect. And you can see that, you know, there was, okay, transect D is a bit of an anomaly, and I'm going to have to talk to John Krause, who I saw is on the call, because I think that sampling transect is across the channel from a tide gate release area. So I think we're seeing high deposition there. But you can see that a few transects aside, most of them had very similar deposition, including the restoration in the back, which is transect A and B. Next slide. So accretion was the feldspar layers again, and they were placed near these transects. And so you can see they're even more similar when looking at the long-term sort of feldspar accretion in the marsh, again, with D being the exception. Next slide. So we did a study in 2022, Jessie Lacy and I, funded by the RMP, to look at sediment flux onto the marsh surface. And that is one of the reasons that working at this location was really important, because we had even more pre-data for 3 of the transects. So we reoccupied those during this study to see, to basically be able to compare. There's going to be so much with interannual variability from year to year based on like what the weather's like that year or how many storms we have. So we were able to look at our previous study of 2022 to what was collected in 2023 to 24. And most of the data collected was not significantly different, with one exception, and that was the Bay transects, where 2024 was significantly different than 2022. But the rest of them, in essence, they were basically the same or not significantly different. Next slide. So the tracer study, we knew one of the biggest challenges of this study was going to be, how do we know if it made it to the marsh, right? There's so much variability from year to year, depending upon the conditions and what's happening in the bay and with the weather, that we tried to throw all these different approaches at this study to see if we could help answer, did it make it to the marsh? So as Jessie's results showed, that the mounds did erode and they did disperse, but not maybe as quickly as I would have guessed. But, this is the first time we're doing this. Some of that sediment did move towards the marsh. Some of it moved in other directions, as Jessie showed. So our second approach was to put in tracer particles. And so this is fluorescent magnetic silt that is engineered by a company called Partrek, who's done this quite a bit in other places. So after the placement was completely done, we deployed sediment tracer out at one of the placement sites. And so this gave us a second tool to see if we could see where this goes. So it is both fluorescent and magnetic. Thanks, Jessie. So I'll show a sampling design for Jessie. So Jessie looked for the tracer in the shallows, and my team looked for the tracer in the marsh. So we sent a subset of all the sediment pads and feldspar collections. We also did surface scrapes across the marsh surface in mudflat. So over 530 samples were sent to Partrek looking for this tracer material. Next slide. So this is what we are just getting this data, like literally got the report a couple of days ago. So we still have a lot to look into, but you can see on the left where the bed sediment samples were collected with Jessie's team, this array across the shallows. And then we had magnets and, like I said, all the scrapes in the marsh. And so we will continue to see what the tracer detection results look like. Overall, it seems to be fairly low. However, we have kind of more to figure out with this, but it's a neat tool. And I think we're going to learn a lot of kind of methodology approaches moving forward in future studies. Next slide. So I kind of blew through that. You guys have been able to see multidiscipline topics, but the fun part is now we're going to all get together and say, what is the big take-home results? So for our part, marsh deposition was highly seasonal. It's nature. It's hard to figure out what are the driving mechanisms for sediment delivery. We had the highest deposition in the summer. Those winds and waves in South Bay really deliver the sediment to the marshes. That's just sort of good to know if we wanted to place anything into the future. The accretion rates measured in these marshes are 1.5 to 2 centimeters a year. So that is pretty darn close to pacing sea level rise, or just a little bit under. So that in itself, I think, is really valuable information and goes to Julie's group of it's a good site selection for sediment nourishment. And so far we have detected a little bit of tracer in the marsh, but not a lot. So we'll continue to analyze that data. Thank you. And I'm passing on to Julie.
I'll try to wrap it up, but I hope you all can see kind of what yes, like Karen said, a multidisciplinary, many types of monitoring, and the data are just coming in as everyone has shown. So our next step as a group is getting all together and really synthesizing this between all the teams, including the eelgrass team. We have another person monitoring Mount Eden Slough. So there's a lot to synthesize to figure out kind of what did this mean? How do we learn from it? How do we improve on it? How do we try this again? I think it's really important as we try these new tools for sea level rise adaptation that we allow ourselves to get some parts right and some parts wrong, and overall try to iterate on these different approaches. One thing to point out that Michael McWilliams, who I see is on the call, pointed out to us a lot during his modeling, which he did early on, is that many of these marshes that we're working on are laterally eroding, are projected to downshift, but are actually quite high in the tidal frame right now. So it's possible that, seeing tracer on the marsh like that was, we shouldn't have expected that really. What we're trying to test is this tool. How do we measure it? How do we make sure to iterate on it? How do we not cause environmental impacts? So I think we're all kind of in this process of figuring out the pilot, and then how does that scale up? Where are the next appropriate places for it to scale up? How does something move from a pilot into practice? How do you iterate on something new? And really, what are our lessons learned from round one that we could apply to a round two? Next slide, please. As you all know, these things take a really long time to do. So we're already starting to think about how do we integrate the findings into something, a next round. We did our initial modeling on Emeryville Crescent, so we're starting to explore what that would look like to try another placement offshore of Emeryville Crescent, which would use material from the Port of Oakland, just around the corner. This is a small eroding marsh. It's also high in the tidal frame still, but there are many partners involved in the Emeryville Crescent right now, including SFEP, East Bay Parks, the city of Emeryville, the city of Oakland, and we're trying to figure out how can we cost share this through some of the new tools that have come through the Army Corps for more beneficial reuse of dredged material. So we're targeting, this would not happen until the summer of 28, so we'd have a lot of time to integrate the lessons learned from this first study. Next slide. There's a lot of lessons learned, including everything that you've heard from the USGS team. Some of the things that weren't touched on are contracting lessons. This was tied to an O&M dredging project, and so we weren't able to control the timing. It would have been great if we could have done this in the summer, but it was done in the winter, and that was purely because of the dredging schedule. So things like that, we're trying to figure out how to maximize on. And then ultimately, which of the monitoring approaches work the most effectively? How do we apply that to another effort? And lastly, I want to end by saying that these pilot projects take so much work from so many people. The huge USGS team, some of these, there's many more names that aren't on the list. Large team at the Army Corps, modeling from Anchor QEA, Coastal Conservancy, BCDC, and the Water Board was our CEQA lead and a huge partner in this. So just want to say pilot projects take a ton of teamwork, and I'm thankful for everybody along for the ride on this one. So we're happy to take questions and more to come. Thanks for the opportunity.
Thanks to what a great set of presentations for the whole team. This is amazing that you were able to get through so much information in such a short amount of time, in like 50 minutes. So I think there were some questions. Dave, did you want to field questions, or do you want me to go ahead and do them?
Well, we do have just a couple in the chat that weren't already addressed. Some were. Tanya Graham from AECOM. Tanya, do you want to ask your question aloud, or would you just like me to read it?
I can ask it.
Nope.
Thank you for including me. I was just curious. I know that Jessie said that she'd be heading out for a year two data point this winter. And I'm curious if Susan's team is also going to be heading out this winter for a year two data point. I'm interested to see how the benthic community energy density has changed since 6-month marker.
Hi, Tanya. It's good to hear your voice. Tanya worked on this study early on and has moved on to a new position. So we miss her, and she did a great job on this, coordinating this study. Right now, we're not planning on doing a 2-year sampling. We're still going through the 12-month results. So I think that's going to be really informative, to see what's happening after that 6-month marker. But as you know, there are a lot of samples, upwards of, nearly 1,000. So we're still working on them. So yeah, thanks.
And Nikki Taylor asked, how deep were the onshore-offshore suspended sediment concentration station measurements? And I didn't hear if that got answered or not.
So that's very similar to the depth of the placement area. So a mean low water depth of about a meter. The water depth ranges actually from about, at the sites, the water depth ranges from about 0.5 meter to 2.5 meters.
Thanks, Jessie. We do have one from Jane that is not really about it's not really about the subject of these talks. Jane Moss, the Pond A1 project is like really different. It's not using dredge sediment and indirect sort of offsite strategic placement. We're trucking material in and placing it directly where it's going to end up, inside of the pond, not out on the tidal marsh. So it's really different, and we can talk offline about that if you want to send a question or something into the Restoration Project's website or something. We can talk about that there. We will be putting together a public walking tour in early October at Pond A1 for any people on this in this meeting who are interested in that. We'll be publicizing that as the date gets closer. And Michael McWilliams, did you get your question answered?
Thank you.
Yep.
By the way, thank you.
Sure.
I just had a question about the bar graphs. I think that Karen said only the bay transect was considered to be significantly different between the 2 years, but it looked like the interior transect was also similarly different.
Yeah, without the graph in front of me, you're right. So significantly, like with the statistics, it was just the bay ones. However, you're right. The interior did show an increase, unless I looked at the stats wrong. Yeah, we're going to look at it more because right now that's just transect average over the whole sampling period, but we can look at it monthly for the similar months. So it does seem like the bay ones are significantly different, but more soon, Michael.
Great, thank you. Yeah, I mean, interior ones tend to be lower elevation than the marsh, so they also are pretty affected by adding sediment into the system.
Yeah.
Like that's probably an easier place to get the sediment to show up than in the Whale's Tail Marsh.
Yeah. So today I just presented like the average for the sampling whole period. So I think teasing out monthly is going to be really important to see if there's certain months that had significant difference.
Thank you.
Yep.
We have a few minutes left if there's other questions or follow-up thoughts, comments.
I'm just going to jump in while people are thinking and add that next month, Josh Ackerman from USGS will be giving a talk on breeding water birds. So if you're interested in what's coming up next, that'll be next month's talk.
Noah, go ahead, jump in.
Oh, I was terrified of the amount of effort required to do that sediment accretion sampling. And I was wondering, are those like just the level of difficulty on that? And then are those destructively sampled? Like when you take a measurement, do you lose that site or can you keep revisiting the same site and get continuing information?
So for the feldspar measurements, usually, because we have them kind of throughout the bay, we normally, honestly, we use like a hunting knife or something and we create a plug. We'll measure it and we put it back.
Okay.
So and we have them in 3 corners. I know I said it's one sampling, but there's multiple corners. We did keep some because we were looking for tracer, but normally we don't. So you're right. It is destructive, but measuring it monthly, like it seemed like we could always find a place that wasn't disturbed.
Gotcha.
It's great because it's very inexpensive. It's low tech and it's out there collecting data for you. And you get back when you can. So I'm a fan of people putting it out in their marshes.
Okay. Thank you.
Yeah.
A couple hands up from Sarah Izat and then Pat Showalter with the 3 minutes we have left. Go ahead, Sarah.
I think Pat was first.
Oh, sorry. I didn't realize that. Okay.
Okay, just quick question. I wondered how difficult was getting the dredger and the scow out there. I know we worried a lot about how shallow the South Bay was where we were doing that. So I wondered, what was the difficulty of that?
Yeah, good question, Pat. I think it was pushing the existing equipment in the bay to the max. And in fact, the scows were brought down from the Pacific Northwest. It was a company that hadn't worked in the bay and they had more light, small scows. And there were these, I mean, I hate to say cute for scows, but they were these little cute 300 cubic yard scows. And then the 1600 foot, but these are not the ocean going scows or not big ones. I think what I'm learning is that the dredging community will respond to these new projects. And so we put that out there. We talked a lot about it and it's work. And I think it's work that is probably going to, hopefully increase as as we really need this. Again, I want to say, I think we're testing this tool for the future, not necessarily to save Whale's Tail Marsh this moment. Since it is high and, Karen is showing these high accretion rates and we knew that going in. I think I've heard through the grapevine that, we said to the dredging community, would you have done this differently? Would you have rather run a pipe? Would you have rather done other things? And I think each time we're going to have to really figure out what's the right equipment, given the individual situation, but they said they would have done it again. And as you saw in Jessie's graphic that she showed, they did visit the same places multiple times, which is not something we necessarily thought because I think we're accessing the places that were easiest to go. So I think our challenge as a community is figuring out how to use that tool, but also maybe there's other ways to get sediment a little bit closer. So
thank you.
I don't know if that helps.
Yeah, no, that's very interesting. Thank you.
All right, Sarah, you're going to bring us home.
Well, maybe not. I'm not sure if you can answer my question. This is a little bit backwards, but I'm just wondering and I don't know whether this study can tell this, but for this is kind of getting at a restoration project, but overall at wetlands, and whether or not the connectivity of the wetland site itself influences how much accretion would occur. So, a lot of the wetlands along the shoreline, there's shoreline modifications, riprap, et cetera, that limits the connectivity. And when someone is designing a restoration project, sometimes that connectivity is also limited, which you may not see in a quote unquote as much in a natural wetland. So when we're designing or looking at wetland restoration projects, it seems intuitively that greater connectivity would lend itself to greater accretion. I'm not sure whether or not you can tell that from this study. And that's why I have this assumption in my head, and I don't know if it's true or not. So that's the question. And sorry, I know it's a little bit off, but
Well, I can comment on that. I don't think we've studied, I agree with your intuition, and we have not done studies where we've compared, like a levied off site where we open one breach and all flows going in and out through the tidal marsh. It makes sense that through the tidal creek, it makes sense that, that is limiting the amount of delivery. So what we have done is a couple studies. So at China Camp and then the Whale's Tail study, to try to look at delivery directly across the bay edge compared to delivery through the tidal creeks. And overall, what we're seeing, because a lot of the literature has really focused on delivery through tidal creeks, and what we're seeing is that the pathway of directly across the bay edge is a very significant source. If you look sort of bay wide, so if you look sort of per lateral meter along the shore, there's more coming across the bay than an individual tidal creek. But if you look at the marsh as a whole, those tidal creeks are feeding the entire interior of the marsh. So the total is greater through the tidal creeks. And that's just at, one or two sites. But anyway, that's the only comment I can make on that. I don't know if Karen has other comments.
Yeah, I think my only additional comment is I agree that your intuition is correct. More connectivity in theory would bring in more tidal waters and more sediment. I mean, we know on the flip side that if a restoration is too choked or constrained, it doesn't get enough sediment and it doesn't accrete as expected or at the rate. I mean, that's just anecdotally from different restoration projects. So I don't think you're wrong. I don't know if the study will help with that, but I don't think your intuition is wrong. Thanks. It's a good question.
I just, when I'm thinking about in future locations to put this, I want to be thinking about and I'm obviously not the main person to be thinking about this, but I want to make sure that the site that we're looking at is actually can accrete the material and has the mechanisms, or is there something we need to do along the shoreline in addition to placing the sediment that's going to facilitate that accretion? So anyway, thank you for
no. And there
is thinking about it. I love that you're thinking about that.
Me too. And I have seen in other California estuaries where they do scrape down that bay wide levee, so it is it is has more kind of tidal influence during the highest tides. They do that in Humboldt quite a bit. Yeah.
And then the other thing happening at some marsh edges on Whale's Tail, as an example, is lateral erosion. So, so when the edge is exposed to all the energy of the bay, it gets sediment and it also gets that erosive energy. So we're measuring accretion, but there's this other part of the budget, which is erosion, which is also happening, so it's just another factor in terms of site selection.
Cool. So I think that's a wrap. So thank you all. Really great, rich presentations with lots of interesting data and information. We're looking forward to all the final work that you guys do. So thank you so much for presenting today. And thanks everybody for joining us. We'll hopefully see you next month.
Thanks for coming, everybody.
Thanks everyone for being here.